and welcome to the very first of our stoichiometry video lectures. I hope you're as excited as I am. Today, our objectives are going to be to review some molar mass. We're going to convert lots of things, mass and moles and particles and moles and volume. We're going to do some multi-step problems at the end. If we're talking about mass and moles and dimensional analysis, we're doing lots of math. Grab a calculator if you don't have one already. We're talking about mass and moles of elements and compounds. You're going to need periodic tables to find those mass numbers. Also, definitely have some paper to take notes on, something to write with, or the outline for today's lecture. So let's talk about molar mass. What even is molar mass? So molar mass is the mass of a mole of a substance, and that's going to be measured in grams per mole. This is the same thing as the mass numbers on our periodic table. The difference is that we're looking at these mole piles of atoms or molecules, not just an individual atom or molecule. If I'm looking at the individual atom or molecule, I'm measuring in AMUs, atomic mass units. That's for one atom of an element, one molecule of a compound. Here we're going to be talking about these big piles of atoms and molecules. The reason that we have these piles, these moles, is because atoms and molecules are very, very, very small. If I didn't have a big pile of them, I wouldn't even notice that they were there. So we use moles in order to quantify these big piles of atoms and molecules. We're going to measure the mass of moles in grams. So when I'm finding the molar mass of a substance like sodium chloride, I'm just going to add up the masses from the periodic table. So sodium chloride, I'm going to write that formula. Sodium is Na, chlorine is Cl. Sodium has a charge of +1, chlorine's a -1, so I don't have to do anything to balance out this formula. To find the molar mass, I'm just going to add the masses from the periodic table. Sodium is here. It is a 22.990. Chlorine's over here. It is 35.453. Handy dandy calculator tells me that 22.990 plus 35.453 equals 58.443 grams per mole. So the molar mass of sodium chloride is 58.443 grams per mole. So now I want to know what's the mass of 1 mole of sodium chloride. What is the mass of 1 mole of sodium chloride? Friends, we already know that because the molar mass is literally the mass of 1 mole. These are the same questions, I'm just asking you in different ways. So the molar mass, the mass of 1 mole, same thing. It's still going to be 58.443 grams. And we can say grams per mole, that's the molar mass. But if I'm looking for the mass of 1 mole, really I just want to know how many grams are in that mole. 58.443 grams in 1 mole of sodium chloride. Let's do one more practice problem together, and then I'm going to have you do a couple on your own. Find the molar mass of nitrogen monoxide. So this one is a covalent compound, not ionic, so I don't have to worry about charges. No prefix here means only 1 nitrogen. Mono means 1, so I also have 1 oxygen. To find the molar mass, I'm just going to add these up. Nitrogen is 14.007. Oxygen is, whoa, I just scribbled right on top of the mass, 15.999. We're going to add those up with our handy dandy calculator. 14.007 plus 15.999 gives us a grand total of 30.006. 30.006 grams per mole is the molar mass of nitrogen monoxide. These ones I want you to do on your own here in the Ed puzzle. So hopefully you figured out that the mass of water, H2O, is going to be equal to 2 hydrogens plus 1 oxygen. And when you add those up, you get 18.015 grams per mole. 18.015 grams per mole. We're going to take those 2 hydrogens, 2 times 1.008, because that's hydrogen's molar mass. There it is. 1 oxygen is 15.999. Good. This one, the mass of copper 1 chloride, might be a little bit difficult because we've got to balance some charges. Copper 1 is copper with a +1 charge. Chlorine is here with a -1 charge. +1, -1. These charges balance out. So my formula is simply CuCl. Cu is here, 63.546. Chlorine is here, 35.453. We're going to throw that into our calculator and get 63.546 plus 35.453 gives us a grand total of 98.999 grams per mole. Good? All right. So now we're going to come back to this idea of what even is a mole. So now we know how to find the mass of a mole, but do we even know what is a mole? A mole is a pile of things. Mostly we talk about atoms and molecules, and there are Avogadro's number of those things in that pile. So Avogadro's number is 6.02 times 10 to the 23rd power. It's on your list of constants and conversions, so you don't need to have it memorized, but we're going to use it so often you will have it memorized. 6.02 times 10 to the 23rd, and we're going to have particles per mole. And those particles, most often we're talking about atoms or molecules, but really we could count a mole of anything. There's just a lot of those things. So we usually just count super small things, atoms, molecules, ions, stuff like that. So Avogadro's number, 6.02 times 10 to the 23rd. How many things are in a mole? Well, there's Avogadro's number things in a mole. There are 6.02 times 10 to the 23rd things in one mole. Things like atoms or molecules or even elephants. How many elephants in one mole of elephants? There are 6.02 times 10 to the 23rd elephants in one mole of elephants. How many cookies in a mole of cookies? There are 6.02 times 10 to the 23rd cookies in one mole of cookies. Keep this in mind as we're moving forward into some dimensional analysis using these numbers. But since we're going to talk about some dimensional analysis, let's review what even is that. These are conversions. So we're going to do some fabulous conversions. We did a lot of these back at the beginning of the school year. We're going to do some more now. So I have to figure out how many milliliters are in 4.2 liters. We always start with our given. Our given is 4.2 liters. I'm going to set up my railroad tracks, and I'm going to figure out how many milliliters are in these liters by putting together my conversion factor. I have liters here on the top. I'm going to put liters on the bottom so that my liters cancel out. I want to turn liters into milliliters, so I'm going to put milliliters on the top here. I need to know how many milliliters are in 1 liter. I remember that there are 1,000 milliliters in 1 liter. So now the magic is liters on top and bottom have canceled out. I'm left with just milliliters, which is good because that's what I'm trying to find. So now I'm going to multiply across the top. 4.2 times 1,000, multiply across the top. 4.2 times 1,000 is 4,200. Divide by what's on the bottom. I only have a 1. So this is easy math. 4,200 divided by 1 is 4,200. My unit label is milliliters because all those liters canceled out. And so my answer is 4,200 milliliters. There are 4,200 milliliters in 4.2 liters. Good. Is it all coming back to us? Good. So let's do another one. We're going to convert 3.0 meters per second to miles per hour. So remember that this slashy line here is the same thing as a fraction bar. Our fraction bars in our dimensional analysis and our railroad tracks, these are our fraction bars. So this and this are the same thing. So I'm going to put 3.0 meters on the top and seconds on the bottom. If you don't like seconds by itself, you can put a 1 in front of there because this literally means that we're going 3 meters in 1 second. So you can throw that 1 if you don't like having no number at all, but that 1 is implied. So now I need to convert to miles per hour. I'm going to have to convert my meters to miles and my seconds to hours. It doesn't matter which one we start with first. I'm going to start with meters to miles first, just because I feel like it. So I'm going to take my meters that are here, put meters on the bottom. I'm going to convert meters to, oh gosh, I don't actually know how many meters are in a mile, but we do know that there are 1,000 meters in a kilometer. So first I'm going to convert meters to kilometers. Meters on top, meters on bottom are going to cancel out. What do I know about meters and kilometers? I know that 1 kilometer is 1,000 meters. 1 kilometer, 1,000 meters. So now my meters, top and bottom, have canceled out. Yay! I have kilometers per second, not even close to what I'm finding, miles per hour. So next up, I'm going to get rid of those kilometers and turn my kilometers into miles using this one conversion factor right here. I have kilometers on top. I'm going to put kilometers on the bottom to get them to cancel out. Miles on the top, because this is what I'm looking for. Kilometers. Kilometers are going to cancel out. What do I know about miles and kilometers? I know that 1 mile is equal to 1.6 kilometers. 1 mile is equal to 1.6 kilometers. So now, kilometers, boom, boom, cancels out. I now have miles per second. Miles! Yay! But I don't want seconds, I want hours. So now I'm going to get rid of my seconds. I have seconds on the bottom. To make it go away, I need to put it on the top, my friends. Seconds on the bottom, seconds on the top to get those seconds to cancel out. What do I know about seconds? I know that there are 60 seconds in 1 minute. So here, voila, seconds. Seconds cancels out. What unit label do I have now? I have miles per minute. I don't want minutes. I want hours. So I need to add one more piece to my railroad tracks. I have minutes on the bottom. I want it to go away. I'm going to put minutes on the top so that my minutes cancel out. I want to turn those minutes into hours. What do I know about minutes and hours? I know that there are 60 minutes in 1 hour. I have minutes and minutes. They cancel out. What unit label do I have left? Friends, we have miles per hour. Miles per hour. We did it! So now we can go ahead and do our calculations. We're going to multiply everything on the top. So handy dandy calculator. 3 times 1 times 1 times 60 times 60 gives us 10,800 miles. Divide by everything on the bottom. So I'm going to multiply the bottom. 1 times 1,000 times 1.6 times 1 times 1. That's going to give us 1,600 hours on the bottom. Remember that this is the same thing as a fraction bar, and fractions mean divide. So our last step, we're going to divide top by bottom, numerator by denominator. 10,800 divided by 1,600 gives us 6.75. 6.75. And always, we do love to use our unit labels in chemistry. So I have miles per hour. Miles per hour. Good. Oh my gosh, almost so good. Let's do oh, this is a bad color to choose. Sig fig check. How many sig figs do I have? I have 2 sig figs here in my original piece of data. I have 3 sig figs here in my final answer. So I'm going to go ahead and convert 6.75 to 2 sig figs. How are we going to do that? I'm going to keep 1. I'm going to keep 2 sig figs. That 5 is going to round that 7 up to an 8. 6.8. Keep that unit label, miles per hour. Final answer. Good work. These are yours to do in Edpuzzle. Good luck. So, start with that given, 2.8 meters. We're going to convert meters to centimeters. I've got meters on the top, put meters on the bottom, put centimeters on the top. There are 100 centimeters in a meter. We're going to multiply the top. 2.8 times 100 is 280. Divided by 1 doesn't even do anything. My meters, top and bottom, cancel out. We're left with centimeters is my unit label. Our final answer is 280 centimeters. How about this one? How many seconds in 0.40 hours? Start with that given, 0.40 hours. We're going to first turn our hours into minutes, unless you know how many seconds are in an hour. How many seconds in an hour? There are actually 3,600 seconds in 1 hour. Hours, top and bottom. Boom, boom, cancel out. What are we left with? 0.40 times 3,600 on the top. 0.4 times 3,600 gives us 1,440 seconds. Divided by 1, but that totally cancels itself out. And so this is our final answer, 1,440. If you don't like this, your other option is to go from hours to minutes. 1 hour is 60 minutes. And then from minutes to seconds, 1 minute is 60 seconds. Our hours cancel out, our minutes cancel out. And then you're going to do 0.40 times 60 times 60. 60 times 60 is the same thing as 3,600, which is how we got that number. All right, so now we're going to go back to some dimensional analysis using these mole things, right? So going back to the molar masses, back to the periodic table, and some dimensional analysis. So what is the mass of 1 mole of carbon? This one's an easy question. We're asking for molar mass, mass of 1 mole of carbon. Look at the handy dandy periodic table. It is 12.011 grams. The molar mass, or the mass of carbon, the molar mass of carbon is 12.011 grams according to our periodic table. What is the mass of 2 moles of carbon? Well, you can just do this. I'm going to take that 12.011 times 2. That's 24.022, right? 24.022 grams if 2 moles of carbon, because 1 mole of carbon is 12.011. But I'm going to go ahead and do this in railroad track fashion just to keep us in that practice. So if I have, oops, that's not what I wanted to start with. If I have 2 moles of carbon, 2 moles of carbon is my given, and I want to convert those moles to grams. I have moles on top. I want moles to go away. I'm going to put moles on the bottom. I want to convert my moles into grams. I'm going to put grams on the top. I know that 1 mole of carbon has a mass of 12.011 grams because the periodic table tells me that it does. So we're going to get that mass from the periodic table. So 12 moles of carbon, oh my gosh, 2. I don't know why I keep saying 12. 2 moles of carbon, 12.011 grams per mole. So now moles top and bottom cancel out. We're left with grams. Handy dandy periodic table tells us that 2 times 12.011 equals 24.022 grams, which is exactly what we got here. Good. So we can do the flip. Start with the mass, start with grams, and convert it into moles. So if I have 6 grams of carbon, 6 grams of carbon, how many moles is that equal to? Well, I have grams on top. I want grams to go away. I'm going to put grams on the bottom. Grams on the bottom, moles on the top. I know that 1 mole of carbon has a mass of 12.011 grams. Notice I put my mass, my gram number next to the G. Moles is still a 1. I'm going to cancel out grams, top and bottom. Boom, boom. What are we left with? 6 times 1 is 6, divided by 12.011, 12.011. And when I do that math, 6 divided by 12.011, we get 0.49954. So many digits. Let's check some sig figs. There are 2 sig figs here. I'm going to keep 2 sig figs down here. I'm going to keep 1. I'm going to keep 2. That 9 is going to roll that 9 up into a 10, which means that our 4 is going to roll up into a 5. So final answer 0.50. What's my unit label? Moles, because my grams canceled out. 0.50 moles of carbon. And I didn't check sig figs on this one. If you're like, why don't we do sig figs on this one? So when I write the number, I don't really know how many sig figs are there. When I write the number as a word, right? So I just kind of went with what we had. Here, we did have clearly 2 sig figs, and so I kept those 2 sig figs. Good. All right. You do these ones on your own. Answer time. So 2.4 moles of silver is our given. We're going to convert those moles to grams. I have moles on top, put moles on bottom, turn my moles into grams. Moles cancels out top and bottom. But what about those grams? Well, silver has a mass of 107.868 according to the periodic table, 107.868 grams per mole. So I'm going to multiply across the top. 2.4 times 107.868 divided by 1 gives us a grand total of 258.8832 grams, but I'm going to keep only 2 sig figs. So keep 1, keep 2. That 8 rolls that 5 up to a 6, and so our final answer is 260 grams of silver. How about this one? 12 grams of helium gas. 12 grams of helium. We're going to convert those grams to moles. I have grams on top. I'm going to put grams on bottom to cancel out. Moles on top because that's what I want to convert to. Handy dandy periodic table tells us that helium has a mass of 4.003 grams per mole. Grams cancels out. Top and bottom, we're left with moles. 12 times 1 divided by 4.003 gives us a grand total of 2.9977. So many digits. I don't want to keep all those digits. I want to keep 1, 2 sig figs. 1, 2 sig figs. That 9 is going to roll that 9 up to a 10, which means we're going to roll that 2 up to a 3. I got ahead of myself there. So final answer 3.0. Unit label is moles because we canceled out those grams. Feeling good? All right, let's take this up a notch. So here we've got some dimensional analysis with Avogadro's number. Remember that Avogadro's number is how many things are in a mole. 6.02 times 10 to the 23rd particles, atoms, molecules, elephants per mole. 6.02 times 10 to the 23rd. So how many atoms of carbon are in 1 mole of carbon? Well, 1 mole of anything is equal to 6.02 times 10 to the 23rd of those things. So how many atoms of carbon in 1 mole of carbon? There are 6.02 times 10 to the 23rd atoms of carbon in 1 mole of carbon. What about, and I should say molecules, sorry. I definitely have a little goof here. How many molecules of CO2, carbon dioxide, in 2 moles of carbon dioxide? I'm going to start with my given 2 moles. I know that 1 mole of anything is equal to 6.02 times 10 to the 23rd. Since I have moles on top, I'm going to put moles on the bottom. I'm going to convert my moles to molecules. I know that there are 6.02 times 10 to the 23rd anythings, like molecules, in a mole of things. So here, my moles, top and bottom, cancels out. I'm going to multiply across the top 2 times 6.02 times 10 to the 23rd divided by that 1 on the bottom, which doesn't even do a lick of anything, right? So 2 times 6.02 times 10 to the 23rd is going to give me 1.204 times 10 to the 24th molecules of CO2. Good. I'm not going to worry about sig figs because, again, I've got a word number here. Let's do another one. So if I have 1.8 times 10 to the 24th atoms of carbon, how many moles do I have? So now let's start with that number, 1.8 times 10 to the 24th atoms, because this is our given. And my question is asking me to convert those atoms to moles. I have atoms on top. I'm going to put atoms on the bottom because I want it to go away. Convert those atoms to moles, put moles on the top. What do I know about atoms and moles? Well, I know that there are always 6.02 times 10 to the 23rd things, like atoms are things, 6.02 times 10 to the 23rd things in a mole. 1 mole is equal to 6.02 times 10 to the 23rd atoms. So my atoms, boom, boom, cancels out. I'm left with moles, which is good because that's what my question is asking me to do with my calculator. Be careful here, my friends, when you are dividing in scientific notation. Either use on the calculator that EE button, the EE button for scientific notation, or make sure that when you divide, if you're using the divided by button, use parentheses around your denominator to keep everything kosher. So on my handy dandy calculator, 1.8 times 10 to the 24th divided by 6.02 times 10 to the 23rd, and I'm going to get a final answer of 2.9900, so many digits. I'm going to keep 2 sig figs, 1 sig fig, 2 sig figs, 1, 2. That 9 is going to roll that 9 up, which is going to roll that 1 up, and so we're going to have 3.0 moles of carbon, 3.0 moles of carbon. Good? All right, these next ones are yours to do in the Ed puzzle. So let's look at some answers. How many atoms of gold and 2.5 moles of gold? 2.5 moles of gold. We can go ahead and throw the AU for the symbol for gold in there. I want to convert moles to atoms. I've got moles on top, put moles on bottom, convert my moles to atoms. And I know that there are 6.02 times 10 to the 23rd atoms in 1 mole of anything. And so now, handy dandy calculator, 2.5 times 6.02 times 10 to the 23rd power gives us a grand total of 1.505. E24, says my calculator. 2 things. I'm going to check my sig figs. 2, I'm going to keep 2. 1, 2, that 0 leaves that 5 of 5. So 1.5. E24 means times 10 to the 24th power. And my unit label, moles, moles cancels out. I'm left with atoms on the top. So my unit label is atoms of gold. Good? All right. the next one that you did on your own, 3.01 times 10 to the 23rd molecules is your given. That's what you start with. Sodium nitrate, it doesn't even matter that it's sodium nitrate because we're turning those molecules into moles. So I've got molecules on the top, put molecules on the bottom to get it to cancel out, turn those molecules into moles. I know that 1 mole of anything is equal to 6.02 times 10 to the 23rd of those things. So molecules top and bottom cancel out. We're going to do some division. I'm dividing with scientific notation. So I'm either going to use the EE button or I'm going to put my denominator into parentheses just to make sure that order of operations does what we want it to do. Handy dandy calculator says 3.01 times 10 to the 23rd power divided by 6.02 times 10 to the 23rd power is, oh my gosh, 0.5. But that makes sense, right? Because our 10 to the 23 is canceling out. 3.01 is half of 6.02. This makes so much sense. But let's check some sig figs. How many sig figs do I need to keep? Oh my gosh, 1, 2, 3 sig figs. And right now I only have 1 sig fig. 1, 2, 3 sig figs. And my unit label is moles because molecules canceled out. And we can throw in sodium nitrate there if we want to, 0.500 moles of sodium nitrate. So now we're going to look at more dimensional analysis and some volume. We're going to throw some volume into the mix here. So one of the things that Avogadro is most famous for is proposing that equal volumes of gases at the same conditions, temperatures, and pressures have equal numbers of particles in them. And we have done a lot of work to figure out that there is 22.4 liters of a gas in 1 mole of gas. So if I have 6.02 times 10 to the 23rd particles of a gas at this thing called STP, then I'm going to have 22.4 liters of that gas. What is this thing called STP, you wonder? STP is here. It is 0 degrees Celsius and 1 atmosphere of pressure. Atmosphere is our unit of pressure. It's just the pressure of Earth's atmosphere at sea level. So it's an easy one. So 0 Celsius, 1 atmosphere of pressure is STP, standard temperature and pressure. Do you have to memorize these? No, because look, they're on our list of constants and conversions. All right, so how are we going to use this? If I have 4.5 moles of argon gas at STP, standard temperature and pressure, how can I figure out the volume? Well, I've got 4.5 moles, and we know that there are 22.4 liters in 1 mole. I want to get rid of moles. I'm going to put mole on the bottom, turn my moles into liters. 22.4 liters, 22.4 liters in 1 mole, 1 mole. So now my moles, top and bottom, boom, boom, cancel out. With my calculator, I'm going to do 4.5 times 22.4 divided by 1, which we can totally skip because it's 1. 4.5 times 22.4 gives us 100.8 liters of gas, argon gas. Quick sig fig check. I've got 2 sig figs. I've got 1, 2, 3, 4 sig figs. Ooh, this one's weird. How do I get rid of the zeros, right? Because the 0 rounds the 0, it's just going to stay a 0. But I need to make it 100, right? But now I have 1 sig fig and I need 2 sig figs. But if I put a decimal point here, now I have 3 sig figs. I need 2 sig figs. What do we do? Scientific notation to the rescue, my friends. We're going to do 1.0 times 10 to the 2, because this is the same thing as 100. 10 to the 2 is 100. So 1.0 gives us those 2 sig figs. 1.0 times 10 to the 2 liters of argon gas is our answer. How about this one? 2.0 liter container at STP would hold how many moles of carbon dioxide gas? We're going to assume we're talking about CO2 gas, STP, standard temperature and pressure. Start with that given, 2.0 liters of CO2 gas. We're going to convert our liters into moles. I've got liters on the top, put liters on the bottom, put moles here because I want to convert my liters to moles. I know that there are back here 22.4 liters. 22.4 liters in 1 mole. Notice 22.4 went on the bottom because liters is on the bottom. 22.4 liters, 1 mole. Liters, top and bottom, cancels out. We get our calculator, and it is 2 times 1 divided by 22.4. And that is going to be 0.08928. So many digits. We're going to keep 1, 2 sig figs. 1, 2. That 2 leaves that 9, a 9. And so our final answer is 0.089 unit label moles of CO2. Good work. These ones are yours to do an Ed puzzle. Remember that. 22.4 liters in a mole. 22.4 liters in a mole at STP. Answers. Hopefully you got 0.032 moles of oxygen gas, moles on the bottom, liters on the top, 22.4 liters in 1 mole, moles on the top and bottom cancel out. 0.032 times 22.4 equals 0.7168. Again, those moles cancel out. We're left with liters as our unit label. Check our sig figs. We get to keep 2. We're going to keep 1, 2. That 6 turns that 1 into a 2. Final answer, 0.72 liters of oxygen gas. This one, I've got 25-liter tank of helium gas. I want to convert that to moles. I've got liters on the top, put liters on the bottom, turn my liters into moles. I know that there are 22.4 liters in 1 mole. Liters cancels out. We're left with moles on the top. 25 times 1 divided by 22.4 gives us 1.116. Lots of digits. I'm going to keep 1, 2 sig figs. 1, 2 sig figs. 1 means that 1 stays a 1. Our final answer is 1.1 moles of helium gas. All right, final problems of the day. We're going to look at multi-step problems. Multi-step problems going from one thing to another thing to another thing. The key to multi-step problems is we always must convert to moles first. Everything goes through the mole. So we can use this dimensional analysis pathway to help us remember these things. So if I'm starting with grams, which is mass, and I want to figure out how many atoms there are. Atoms are particles, atoms, molecules over here. To get there, to go from mass to particles, I have to first convert to moles and then to particles. We always convert to moles and then to whatever else I want to find. So step 1, I'm going to go from 6 grams of carbon. I'm going to convert my grams to moles first. 12.011 grams per mole. Because I'm looking at grams, I want to use the periodic table to find the molar mass. Get rid of grams, top and bottom. Woo, I missed the G. Get rid of grams, top and bottom. Turn those grams into moles. 6 divided by 12.011 gives us 0.4994. So many digits. We're not going to check sig figs yet. It's best to check sig figs at the very, very, very end of the problem. Moles of carbon. So now I want to take these moles and turn my moles into atoms of carbon. So those 0.499542, lots of digits that are still saved in my calculator, moles of carbon, convert to atoms of carbon. I've got moles on the top, put moles on the bottom, put atoms on the top. I'm going to remember that there are 6.02 times 10 to the 23rd atoms in 1 mole of anything. 6.02 times 10 to the 23rd particles in a mole. So now we can cancel out those moles top and bottom and do that math. For 0.49954, numbers that are still saved on my calculator, times 6.02 times 10 to the 23rd power gives me 3.0072, so many digits, times 10 to the 23rd atoms. Now, because I'm at the end of my problem, I'm going to go ahead and check my sig figs. Keep 2. That 0 is going to leave that 0 as 0. So I get 3.0 times 10 to the 23rd atoms of carbon in 6 grams of carbon. Good? All right. We're going to do this one together, and then the next one will be yours to do an Ed puzzle. So 3.01 times 10 to the 23rd molecules of sodium nitrate is equal to how many grams of sodium nitrate? So we're starting here at particles. I want to turn my particles into into grams. Mass grams is over here. To do that, I first have to convert my molecules to moles and then convert my moles to grams. So step 1, convert those 3.01 times 10 to the 23rd molecules of sodium nitrate into moles. We always have to go to moles first. I have molecules on the top, put molecules on the bottom, convert those molecules into moles. I know that there are always 6.02 times 10 to the 23rd molecules of anything in 1 mole of it. So we have successfully canceled out molecules. The last slide, I did step by step each calculation. Here I'm going to mash all my calculations together into one giant railroad track. So I'm not going to do anything with my calculator yet, but instead I'm going to get rid of my moles. I've got moles on top. I don't want moles. I want grams is my final answer. I've got moles on top. I'm going to get rid of it by putting moles on the bottom. Put grams on the top. Now my moles, top and bottom, will cancel out. I'm going to convert to grams. 1 mole is how many grams of sodium nitrate? Well, I'm going to have to go look at my periodic table. Sodium is 22.990. Nitrate is NO3. So that's 1 nitrogen, which is 14.007, and 3 oxygens, which is 15.999. So if I add all of these up, 22.990 plus 14.007 plus 3 times 15.999, again, because I've got sodium nitrate, NaNO3, hands it into calculator gives me 84.994 grams. 84.994 grams. So now I can go ahead and do all my calculations because I have grams. Molecules canceled out, moles canceled out. We're left with grams. Grams is what I'm trying to find. We did it. Calculator time, 3.01 times 10 to the 23rd power times 1 times 84.994 because we multiply everything on the top. Now I'm going to divide by what's on the bottom, divided by, make sure you use your parentheses, 6.02 times 10 to the 23rd, because I have scientific notation in the denominator, and my final answer is 42.497 grams. Sig fig check. I've got 1, 2, 3 sig figs, 1, 2, 3, 9 turns that 4 into a 5, 42.5 grams of sodium nitrate is the mass of 3.01 times 10 to the 23rd formula units of sodium nitrate. We did it. This one is yours to do on your own. I'm going to give you some hints though. Start with your given, convert that given to moles. We're going to go from mass to moles. You do that by using the molar mass. It's on the periodic table. Oxygen is part of Brinkelhoff. So think about what that means. What does that mean for oxygen gas? Once you have moles, then you can convert to molecules of oxygen gas. Remember that there are 6.02 times 10 to the 23rd molecules in a mole. Go! All right, so hopefully you did 6.02 grams of O2 because oxygen is diatomic because Brinkelhoff says so. We're going to convert to moles first. We're going to get rid of those grams. Grams on the bottom, moles on the top. Use the periodic table. Oxygen is 15.999, but there are 2 of them because it's O2, so that is 31.998 grams per mole. Grams cancels out. Boom, boom. Now I've got moles. I want to get rid of moles and turn my moles into molecules. How do I do that? I'm going to go from here to here using Avogadro's number. I have moles, I have molecules. I know that there are 6.02 times 10 to the 23rd molecules in a mole of anything. So now, moles, boom, boom, canceled out. What are we left with? Calculations. I'm going to do 6 times 1 times 6.02 times 10 to the 23rd divided by everything on the top. Oh, sorry, not divide, multiply. Multiply by everything on the top and then divide the bottom. So 6.0 times 1 times 6.02 times 10 to the 23rd divided, oh gosh, I pushed wrong buttons on my calculator. Let me try again. 6.0 times 1 times 6.02 times 10 to the 23rd gives us 3.612 times 10 to the 24th. Divide that by 31.998. 0.998. And calculator says 1.1288, lots of digits, E23. I'm going to keep 1, 2 sig figs, 1, 2 sig figs, that 2 stays that 1 at a 1, 1.1. E23 means times 10 to the 23rd power, and my unit label is molecules. Molecules of O2. Oh gosh, I just missed the answer. We're getting tired, right, my friends? This was big. This was big math, big brain. But we finally made it to the end. So great work for sticking it out all the way to slide number 22. Mass, moles, and dimensional analysis. We reviewed molar mass. This is the mass on the periodic table. To convert between mass and moles, we need to use that molar mass on the periodic table. To convert between moles and particles, we need to use Avogadro's number, 6.02 times 10 to the 23rd. To convert between moles and volume, we need to use the molar mass of an ideal gas at STP, 22.4 liters per mole. And then dimensional analysis, multi-step problems, we always convert to moles first.